In this video, we're going to be talking about linear regression models, line of best fit, however you want to call it. I'm just going to explain what's going on in this little Excel file y'all were given, plus one example from the PowerPoint. This is chapter 15, BIT. Let's get into it. So here, we're given a chart with quarters in different years and the demand in thousands per quarter. So the demand per quarter given in units of 1,000, we have totals for different years, totals for each quarter in different years, whatever. So hopefully the totals make sense. That's nothing crazy. Total for everything, whatever. Now, linear trend line forecast for year 4. What they're describing is when we look at these 3 rows here, specifically like in year 1, the total demand was 45. In year 2, the total demand was 50.1. In year 3, 53.6. Over time, we can see that the demand is increasing. Now, if we were to plot these 3 points essentially and create a line of best fit, and then use that line, use that relationship between y and x to plug in 4 for x, plug in year 4 for x and see what the y value is, they're saying that y value would be 58.17. So we're going to do just that. I'm going to ignore all the ways they do it in the PowerPoint because you don't have to know how to do it by hand. Maybe you do. Maybe they want you to do it by hand. But I mean, if your work is not being checked on this exam, who cares? So I highlighted these. It's like we have x values corresponding to y values essentially. So they're different years and they're different total demands for the year. You can see these points form a very linear situation. So we click on this chart, we go to add chart element, go to trend line, more options, and you click on this if it's not already there. Linear, so we're putting a line of best fit through these points, and then you hit display equation on the chart. Also, I would recommend clicking, if it doesn't go away, what the hell is this? Why does it do that? Let me go back to it. Trend line, more options, this, display equation, and then display R squared value. So we'll talk about this in a moment as well. First, let's talk about this. So, where did my graph go? Here we go. So line of best fit, equation of that line, R squared. So they say step 1 is computing the components of the linear regression equation. So this is the linear regression equation. So we should see these values roughly here. So what do we have here? We have that B is 1.25 and, oh wait, sorry, this is the wrong, oh, I'm so stupid, I'm sorry. That's for the next one. Forgive me. Okay, I forgot what I was doing for a sec. Anyway, we have this equation. And again, the idea was to plug in 4 in place of x and see what the y value is. So that's what we're doing. My bad. That threw me off so bad. Because I was like, these answers are not even close. So we're just plugging in this x value of 4. And the idea is like, this should give us the prediction of the demand in year 4. And it's 58.16, 0.17, whatever, and that's this. So that's where they got that. Now, I'll talk about R squared in the next example. Sorry, I mixed up my examples. SF1, SF2, SF3, SF4. So all of these are regarding the different quarters in the different years. And I'm pretty sure they just like show what they're doing here. So it's like finding a percentage basically. So basically, in year 4, if the predicted total demand is 58.17, then it must be the case that that 58 has to be split up amongst the different quarters, right? It can't all just be, demanded in quarter 1 that they have 58. It's 58 split up amongst 4 quarters, just the same way that like this 50 is split up between 4 quarters. Anyway, so what they do is it's sort of like using the average, I don't know, but so they're taking the total demand, say in quarter 1 of all 3 years, dividing it by the total, and what that's giving us is a percentage of this total that was demanded in quarter 1. Okay, so it's 42 divided by that, and then they multiply that percentage by the total demand. So it's like telling us what percentage roughly quarter one takes up of the total, multiplying it by this total to get that. So that's what they're doing. So 42 divided by that times this gives us that. And they repeat that all the way down just with the different quarters. So this quarter total divided by that times the total gives us this, and so on and so forth. So they do it here, they do it here, and they do it here. That's it. That's all I want to talk about with that one. Now, here we go. In the PowerPoint, they ask you to do something with this example here. So we have quarters, 1 through 10, building permits, lumber sales, X and Y, respectively. Okay, so step one is computing the components of a linear regression equation. So we're using X and Y and coming up with our linear regression equation. So we highlight those, we get an insert scatter. We can see that these kind of have a linear relationship. So we're going to add chart element, go to trend line, more options. We're going to do a line of best fit. So display equation on chart for linear, display r squared. Now it's this r squared that we're going to talk about in just a moment. So now we can see our components. Our y equals mx plus b, which they're going to call something slightly different. Let's see what they call it. They call it a plus bx. So basically bx plus a. Bx plus a in their example here is 1.25x plus 1.36, 1.25x plus 1.34. Excel did it slightly differently. Maybe it's a rounding thing. I don't know. Maybe they did it wrong in the PowerPoint. I trust Excel. Maybe I typed something in wrong, but I don't think I did. So this is our linear equation. So what they just did by hand, which again, I don't think you have to know how to do that. I think just know how to use Excel. You can get doing this. Now, correlation coefficient. Correlation coefficient is an R value, not R squared, but R value. And it's a number that tells you how strongly correlated the two variables X and Y are. The more correlated they are, the more linear natural behavior they have. So like basically if R is a strong correlation, then these points would literally form a line. And you can see that they kind of form a line, but these points aren't necessarily on the line. They're near the line, not on it. So we can find that R value in Excel as well. We could either take the square root of this to get R, because this is R squared, right? Or we could use a different function. So I'll do two different ways. Again, we can do the square root of R squared, so 0.8565. We get this, so that is our R value. Another way we can find R is using a function in Excel called correl. Correl calculates the correlation coefficient between two data sets. So two data sets being this, X, put a comma, and then all the Y values. Hit enter, and we get that. So R value using correl, R value using square root of R squared, same thing. So 0.925, that's a very good R value. It's a very strongly correlated, X and Y data, whatever. I know it's strong because the closer that R is to 1, the more correlated the data is, more strongly correlated X and Y are. 1 is like if you get a 1, that means that X and Y literally form a line. So the R value spans or ranges from -1 to 1. So if the data has an R value of 1 or -1, it's a literal line. It's a positive slope line or a negative slope line. That takes me to talking about like if it's going from -1 to 1, then basically like negative R values indicate negatively correlated data, negative sloped data, right? The closer the data is, the closer the R value is to 0, the less correlated the data is. So if I plotted these points here and just got like the most random scatter plot, like point here, 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 that would be likely something close to a 0 for the R value. So the least correlated, the less correlated it is, the more scattered it is, it leads to an R value closer to 0. The closer to 1, the stronger, more linear the data is. Okay. Negative R values mean negative slope. That's about it. Let's see what else they talk about. Calculate the forecast at x equals 10. So x equals 10, they're really just saying like 10 is the number of permits, right? So yeah, 10 permits. So it's, again, it's just plugging in x here and calculating the y value to approximate whatever their y value is. I don't even remember lumber sales. So if you have 10 building permits, you need that much lumber. That's what it's approximating. There's one more thing I wanted to talk about, and it was the r squared. I thought they had it on here. I think it's back up a little bit. Hold up. Let me find it. There it is. Coefficient of determination. So we just talked about these things, but this is the name for r squared. So r squared is the coefficient of determination. And you can recognize like when they're asking for r squared, because a lot of time they'll say the percentage of the variation in the dependent variable that results from the independent variable. So again, they could say the proportion of variation in y that results from x, or the percentage of the variation in y that depends on x, whatever. That's r squared. And you can compute the r squared, the coefficient of determination, by squaring the correlation coefficient r. So again, r squared, you get the idea. The closer r or r squared is to 1, the more correlated the data is. That's about all I got. All right. So again, they use different methods to get there, like slope and y-intercept and all that stuff. You don't have to use those methods, but you could, I guess. That's about all I got. It's a brief summary. Hope that helps. All right. Bye-bye.